In 1957, Soviet engineers designed a bomber that could strike Washington, D.C. from Siberian bases in under 3 hours. Flying at the edge of space where few interceptors could reach it. The DSBLK wasn't just fast, it was revolutionary. Mark 2.88 capability, 114,000-foot ceiling, 15 tons of nuclear payload. The hypersonic flying wing reached preliminary design and wind tunnel testing before vanishing into classified archives. Had it flown, SAC's entire nuclear strategy would have required fundamental re-evaluation. Most aviation enthusiasts have never heard its designation. Today, you'll discover why this forgotten Soviet superweapon could have rewritten Cold War history and why its DNA lives on in today's hypersonic arsenals. October 1957, Sputnik orbits overhead while American B-52s lumber towards Soviet airspace at 500 miles per hour, subsonic sitting ducks in an increasingly lethal sky. The Strategic Air Command's nuclear deterrent was built on a simple premise. Overwhelm Soviet defenses with massive bomber formations. But what if one enemy aircraft could accomplish what an entire wing of B-52 struggled to achieve? The message was clear. Speed meant survival. Speed meant first strike capability. Speed meant victory. America's answer was the B-58 Hustler Mach 2 revolutionary. And already looking vulnerable because in Moscow, aerospace engineer Alexander Moskalev was sketching something that would make the Hustler seem pedestrian by comparison. The DSBLK, Long-Range Strategic Bomber Flying Wing. Moskalev wasn't just another aircraft designer. By the 1950s, he'd already pushed boundaries with unconventional tailless configurations and advanced aerodynamic concepts. His reputation for visionary thinking made him the perfect choice for the Soviet Air Force's most ambitious project. Strategic Air Command's nightmare scenario wasn't just Soviet missiles. It was a bomber operating beyond the reach of most interceptors, carrying devastating payloads, flying at altitudes where traditional defenses struggled to function. The Pentagon knew the Soviets were working on something revolutionary. They just didn't know how close it was to becoming real. Have you ever wondered what keeps defense planners awake at night? It's not the weapons they can see coming. It's the ones operating beyond their ability to respond effectively. Forget everything you know about 1950s bombers. The DSBLK operated by different rules entirely. 6 VK-15M turbojets arranged in twin triple-engine cells provided the foundation. Later design iterations proposed even more exotic power plants. Combinations of turbojets, ramjets, and afterburning thrust chambers that could theoretically push future variants beyond the initial Mach 2.8 design target. Target velocity Mach 2.8 sustained cruise, a groundbreaking leap in 1950s aviation technology. Service ceiling 35 kilometers 114,000 feet, likely at the edge of space where the atmosphere was so thin the conventional radar struggled to track targets and most interceptors couldn't operate effectively. To put this in perspective, today's commercial jets cruise at 35,000 feet. The legendary U-2 spyplane operates at 70,000 feet. The DSBLK that would soar 44,000 feet above even that rarefield air in a realm where only the most advanced interceptors like the emerging F-106 Delta Dart could theoretically reach. But even then, with severely degraded performance, the aircraft itself defied every convention in the book. A pure flying wing 49 to 52 m long with a 36 to 38 m wingspan. No traditional fuselage, no tail surfaces, no vertical stabilizers. Everything, engines, payload, crew compartments, fuel systems, integrated into one seamless aerodynamic structure, optimized for high-speed, high-altitude flight. Ever wonder why flying wings were rare in the 1950s? The answer lies in stability and control. Without a tail, these aircraft required complex flight management systems that challenged the technology of the era. Pilots described early flying wing prototypes as extraordinarily difficult to control. But Moskalev's team believed they'd address the fundamental control problem through innovative aerodynamic design, mechanical stability augmentation systems, and careful center of gravity management. Wind tunnel testing suggested the DSBLK would be manageable, though the true test of hypersonic control remained unproven. This wasn't just an aircraft. It was a space-age predator designed to hunt from the thermosphere itself. At cruise altitude, the DSBLK would operate in an environment where air pressure was less than 1% of sea level. Traditional piston engines would fail instantly. Even advanced jet engines would struggle. Only the most sophisticated turbojets could function in this near-vacuum environment. At Mach 2.8, aircraft skin temperatures soar beyond 1000 degrees Fahrenheit, hot enough to weaken aluminum, stretch steel, and challenge conventional aircraft materials within sustained flight profiles. The solution was selective titanium construction for critical heat-stressed areas combined with advanced aluminum alloys for the primary structure. With a takeoff weight of 250 to 280 tons, the DSBLK represented cutting-edge material science. Unlike America's later SR-71 program, which required covert titanium purchases through shell companies to avoid Soviet export restrictions, the USSR controlled substantial titanium reserves, enabling domestic production of this revolutionary bomber. The DSBLK's advanced construction, it wasn't just about heat resistance. The materials allowed for structural designs that balanced weight and strength in ways conventional metals couldn't achieve. The flying wing construction required precise weight distribution to maintain stability. Advanced metallurgy made this achievable. The crew of 3 operated from separate pressurized compartments designed for sustained operation in near-vacuum conditions. 2 pilots occupied the forward section with advanced flight controls and navigation systems. Behind them, a weapons system officer managed the nuclear payload and defensive armaments from a dedicated combat compartment. Each crew position featured ejection seats specifically designed for extreme altitude escape. Though at 114,000 feet, survival prospects were minimal even with the most advanced life support systems of the era. But the DSBLK's true terror wasn't its exotic construction or extreme operating environment. It was the devastating payload concealed within its aerodynamic frame. The DSBLK's internal weapons bay could accommodate 15 tons, 33,000 pounds, of thermonuclear ordnance, significantly more destructive power than contemporary bombers like the B-52 could deliver with equivalent range and speed. External hard points on the wing surfaces provided mounting points for additional tactical nuclear weapons or conventional munitions. Do the math. A single DSBLK could carry more nuclear firepower than multiple conventional bombers, deliver it with precision, and escape before most defensive systems could react effectively. The mission profile was Pentagon planners' reoccurring nightmare. Take off from remote bases like Pletk or Boner. Climb to operational altitude in minutes. Accelerate to hypersonic cruise speed. Penetrate U.S. airspace with minimal radar signature. Deliver payload with surgical accuracy. Then egress at Mach 2.8 before SACE could effectively intercept. Flight from Siberia to Washington, D.C. approximately 2.5 to 3 hours. Warning time to NORAD drastically reduced compared to conventional bomber threats. While emerging Soviet SA-2 missile systems and improving radar technology posed potential challenges, the DSBK speed and altitude would make interception extremely difficult with 1950s defensive capabilities. K launches nuclear-tipped cruise missiles, each targeting key vessels in the formation. The missiles strike toward their targets, skimming to avoid detection until the final approach phase. By the time the Enterprise's radar operators register the full threat and coordinate defensive measures, the DSBLK is already racing away at Mach 2.8, climbing back to cruise altitude and potentially preparing for secondary targets. Total mission time under 4 hours. Strategic impact. America's premier naval power projection capability severely threatened with minimal advanced warning. Now scale that scenario to major population centers. New York, Washington, Chicago, all within range of a single sortie with dramatically compressed response times. The scenario troubled Navy and Air Force planners for years even after the DSBLK program was terminated because they knew it pushed 1950s technology to achievable limits. The bomber gap wasn't just about numbers. It was about revolutionary capability. One DSBLK could accomplish what conventional bomber formations struggled to achieve. Near guaranteed penetration of enemy airspace with extreme difficulty of interception. The technical challenges of building the DSBLK were immense, but represented achievable advances in 1950s technology. Propulsion systems had to operate efficiently across a wide speed range from subsonic takeoff speeds to Mach 2.8 cruise. The solution involved sophisticated intake systems that could adapt to different flight regimes, concepts that would later influence advanced aircraft design. Fuel systems required innovative approaches. At high speeds, fuel could serve dual purposes as coolant for critical systems before combustion. Special fuel formations with enhanced thermal properties were developed to prevent complications from frictional heating. Navigation at 114,000 feet presented unique challenges. Standard radio navigation aids were unreliable at such altitudes. The DSBLK would have relied on advanced internal navigation systems. Cutting-edge technology in the 1950s combined with celestial navigation backup systems. Most critically, the aircraft required thermal management systems pushing beyond existing capabilities, active coolant using fuel circulation, heat-resistant materials for critical components, and careful aerodynamic design to minimize thermal stress points were all necessary for sustained high-speed flight. The Soviets weren't starting from scratch. Earlier projects like experimental high-speed aircraft and advanced variants of existing designs provided valuable data on high-speed high-altitude flight characteristics. So why didn't this aerospace revolution materialize? The answer lies in the intersection of technology, strategy, and economics. While Moskalev refined his hypersonic flying wing through preliminary design and wind tunnel testing by 1960, chief designer Sergei Korov was perfecting something even more strategically transformative. The R-7 Amorka, the world's first operational intercontinental ballistic missile. The strategic calculus was compelling, and ICBM could accomplish similar missions with dramatically different parameters. Launch to impact in 30 minutes, zero crew at risk, minimal maintenance requirements, and launch from hardened underground silos that were nearly impossible to destroy preemptively. Why build a complex advanced bomber requiring exotic materials, specialized crew training, and vulnerable airbases when ballistic missiles could deliver equivalent warheads more reliably and economically? The DSBLK also faced significant technical realities. Sustained high-speed flight generated thermal and structural stresses that pushed existing material science. Required cooling systems were at the theoretical edge of capability. The stability and control systems, while innovative, remained unproven at operational speeds. Economic factors played a crucial role. The DSBLK would have been extraordinarily expensive to develop and operate. Each aircraft would require advanced materials, specialized manufacturing techniques, and extensive support infrastructure. With the Soviet Union investing heavily in space programs and ballistic missile development, the hypersonic bomber represented an increasingly expensive solution to strategic problems that missiles could address more cost-effectively. Most critically, the strategic landscape was evolving rapidly. Nuclear doctrine was shifting from bomber-delivered weapons to missile-based deterrence. The age of manned strategic bombers was transitioning just as the technology reached theoretical maturity. By 1960, after extensive preliminary design work and wind tunnel validation, the DSBLK program was quietly terminated. Advanced testing was halted. Design documentation was classified at the highest levels. The hypersonic flying wing became a footnote in Soviet aerospace history, but its influence didn't disappear. Elements of Moskalev's revolutionary design appeared in later programs. The Scion-RSR reconnaissance aircraft incorporated flying wing principles, advanced Tu-95 variants, explored high-altitude operations, and early Soviet aerospace concepts. They borrowed heavily from DSBLK aerodynamics. Innovation rarely vanishes completely. It evolves, adapts, and resurfaces when technology and strategy align. Today's hypersonic weapons trace their conceptual DNA back to programs like the DSBLK. Russia's Avangard hypersonic glide vehicle operates at Mach 20, far faster than Moskalev's bomber, but following similar strategic logic of speed, creating operational advantage. China's DF-17 combines ballistic missile delivery with hypersonic glide technology, creating weapons that can change course during flight and strike targets with compressed warning times. America's proposed SR-72 son of Blackbird targets Mark 6 sustained cruise, finally achieving and exceeding the performance goals Soviets set in 1957. All echo Moskov's core insight, speed, and altitude create operational realms where traditional defenses face severe challenges. The aerodynamic principles pioneered for the DSBLK influence subsequent developments. Flying wing research continued globally, eventually producing aircraft like the B-2 Spirit. The X-47B, unmanned combat aircraft, uses tailless designs explored in programs like the DSBLK. Modern aerospace vehicles reflect aerodynamic concepts originally designed for high-speed atmospheric flight. Modern stealth technology adds another dimension to the DSBLK legacy. Imagine a high-speed flying wing with radar-absorbing materials and carefully designed surfaces to minimize electromagnetic signatures. The result, it would be an aircraft extremely difficult to detect until weapons realize, representing the evolution of strategic bomber concepts. Had the DSBLK achieved operational status, Cold War dynamics would have shifted significantly. While America's nuclear deterrent through hardened missile silos and mobile submarine platforms would have maintained mutually assured destruction, the DSBLK, it would have forced major re-evaluation of U.S. air defense strategies and bomber intercept capabilities. The psychological impact would have been profound. American defense planners would have faced a visible fast-moving threat that compressed reaction times and challenged existing defensive systems, making the abstract threat of nuclear warfare more tangible and immediate. Was the DSBLK technically feasible? The evidence it suggests yes. The Soviets possessed advanced material science, sophisticated aerodynamic expertise, and compelling strategic motivation. They lacked only perfect timing and sustained political commitment as strategic priorities evolved toward ballistic missiles. Could it have fundamentally influenced Cold War dynamics? Consider this. A successful DSPK program might have accelerated American development of advanced interceptor systems and high-altitude surface-to-air missiles, potentially preventing other strategic developments. The ripple effects through defense spending and technological priorities could have been substantial. The aircraft that never flew often influences military planning more than operational systems. As hypersonic weapons proliferate globally with Russia, China, and the United States, all developing advanced high-speed delivery systems, we're witnessing concepts that echo Moskolov's revolutionary vision. Modern warfare increasingly operates at the edge of space where speed creates operational advantage and compressed response times challenge traditional defensive concepts. The DSBLK was simply decades ahead of technological and strategic alignment. Today's defense planners face evolved versions of challenges their Cold War predecessors confronted. How do you defend against weapons that operate beyond conventional countermeasure capabilities? The question remains as complex now as they were in 1957.